This is the third section of this series of lectures. And today, I want to superalgebras. Some references. The theory of these superalgebras. It is a lecture notes. The second reference is qualities representations of these superalgebras. Chain and line. And the third one is these superalgebras. And enveloping algebra. By almost. Let's start with a definition. Is a vector space V is a superspace if there exist two subspaces V0 and V1 of V. And V0 direct sum V1. So a superspace is just a vector space with a decomposition to two subspaces. V0 is called the even part, and V1 is called the odd part. If X is an element of VI, when I is 0 and 1, we say X is homogeneous of degree R and white degree X. One of the audiences have okay. Okay. One of the microphone was on. Yeah, it's not that. Okay. We have different examples of superspaces. Let's look at some of them. m plus n matrices with entries in F. Consider the elements as blank matrices like A, B, C, D, such that A is m times m, B is n times n, B is m times n, and C is n times n. Then I can write V as V0, direct sum V1, where V0 is the set of all elements in this form. And V1 is the set of elements of this form. C is m times n, and V is n times n. And so we have a decomposition of V into two subspaces, V0 and V1, and so V is a superspace. Let's look at another example. Assume V is a superspace and set H to be the set of all linear homomorphism from V to, let's suppose that we have two superspaces and set H to be the set of all linear homomorphism from V to W. We define H1 to be the set of all T belonging to H, such that T V0 is a subset of V0, and T V0 is a subset of W0, and T V1 is a subset of V1, and define it is H0, and define H1 to be the set of all elements of H such that TV0 is a subset of W1 and TV1 is a subset of W0. T is a map from V to W. We consider H0 to be the set of all linear homomorphism that maps V0 to W0, V1 to W1. And H1 is the set of all linear homomorphism maps V0 to W1 and V1 to W0. Okay? And I claim that H is H0 direct sum H1. And if I prove it, in fact, I prove that when we have a superspace, linear homomorphism from V to another superspace is again a superspace, right? Okay. To show this claim, suppose that C is an element of H. So for V belongs to V, CD is an element of W. And W is W0 direct sum W1. So there exists a unique CV0 belongs to W0 and CV1 belongs to W1 such that CV equals CV0 plus CV1. Okay? Each element of W has a unique expression as a summation of two elements, one in W0 and one in W1. Now define T0 from B to W and C1 from B to W. I map B, depending on V is an element of B0 or an element of B1. If V is an element of B0, I map V to CV0. And if V is an element of B1, I map this V to CV1. And for T1, I get an element of V, and again, depending on V is an element of B0 or V1, if V is an element of B0, I map V to CV1, and if V is an element of V1, I map it to CV0. Okay, and I claim that this T is exactly the summation of this T0 and this T1. We have two linear transformation from D to W, and if we want to show that these two linear transformation are equal, it's enough to get one element and show that the both are the same at that element. Okay, so for all V belongs to V. But V is the direct sum of V0 and V1, so it is enough to show this for V when it is an element of V0 or it's an element of V1. If V is an element of V0, we have CV equals, we had this here. Let me call it a star. Using a star, CV is CV0 plus CV1. But CV0, we look at this, CV0, my V is an element of V0, so TV0 is T0V. And again, my V is an element of V0. And when V is an element of V0, CV1 is T1V. So here we have T1V. So if V is an element of V0, I prove that T on V equals T0V plus T1V. Now we need to show this for V belongs to V1. If V is an element of V1, then CV, again using a star, is CV0 plus CV1. But here, my V is an element of V1. And when V is an element of V1, CV1 is T0V. So I have here T0V. And when V is an element of V1, CV0 is T1V. we have T1b here, which is T0b plus T1b. And then I prove the claim. So if we have two superspaces, the linear homomorphisms are also form a superspace. Okay, now let's look at another definition. Suppose that A is a vector space that I want to be a superspace. And a star from A times A to A is a bilinear map. Say A together with a star is a superalgebra if this star is compatible with this decomposition in this sense. If AI a star AJ is a subset of AI plus J, for IJ belongs to 0 and 1, and I consider it as a Z2, the two elements group. Okay, so this summation has meaning. I consider it as Z2. So it means that A0 is a subset of A0, A1 is a subset of A0, A1 and A1 is a subset of A1. Okay, and this is the definition of a superalgebra. And I just want to mention that sometimes I forget about this star and just write AB instead of A star B just for simplicity. The superalgebra is called unital if there is an element that I call it 1 or 1A, if I want to emphasize an A, belong to A, such that A star 1 equals 1A star A equals A for all A belongs to A. And it is trivial that if an algebra is unital, this element is unique, right? The superalgebra A star is called associative in the usual sense if A star B, A star C equals A star B, A star C. We say the superalgebra A is super commutative if A star B equals, when we say anti, you remember from the last lecture that we need a minus here, but this super means that a guy appears here, A, B, when A, B are elements of A0 union A1. So, anti-supercommutativity. A star B equals -(-1) degree A degree B, B star A. And we say the superalgebra A star satisfies the Jacobi superidentity if you remember Jacobi identity, but I say Jacobi superidentity if A star B, A star C equals A star B, A star C minus -(1) degree A degree B, B star A star C. If you forget about this minus, then it is just the definition of Jacobi identity. Okay? Let's look at some example. Set A to be m plus n, m plus n, all matrices of dimension m plus n over F. Where m and n are two positive integers. And we saw that this A is a superspace. I showed you that A equals A0 direct sum A1, and you remember what is A0 and A1, and I just use the usual matrix product, and with the usual matrix product, it's just a unital associative superalgebra. A together with usual product is a unital associative superalgebra. The identity matrix is the unit of this associative algebra. Okay, let's look at another example. Suppose that E is a vector space, which is a superspace, and set C0B to be F of field. You remember I told you whenever I I'm talking about a vector space without mentioning the field. I assume that V is a vector space over F, and F is algebraically closed and of characteristic 0. T0V is F. I put it like this, and T1V is V. I set T2V to be the tensor product of V over F. I don't write it. You know that I'm talking about the tensor product over the field F. And if we look at this T2V, I can write it as T2V is T2V 0, direct sum T2V 1, where by T2V 0, look at this, V is V0, direct sum V1, and this V also is V0, direct sum V1. So we have V0 tensor V0, V0 tensor V1, V1 V0, V1 V1. So I can define T2 V0 to be V0 tensor V0, direct sum V1 tensor V1, and T2 V1 to be V0 tensor V1, direct sum V1 tensor V0. So if we have a vector space, T2V is also a vector space, right? And then we can define C and V in general. C and V tensor V, which is tensor product of V n times, and again, C and V is a superspace 0. C and V 1, and you can realize that what is C and V0? C and V0 is just VI1 tensor VIN, when I1 up to IN are elements of 0, 1, and their summation is 0. And C and V1 is VI1, VIN. It's better to write it in this way. And T and V1 is summation of n belongs to 0, 1, I1, IN is 1, VI1, so VIN, right? So when we have a superspace, we have T0V, which is just the field, T1V, which is V, and T and V, in the way that I told you, it is a tensor product of V with itself and times, and it is again a superspace. And now I set C to be summation of CIV I from 0 up to infinity, and it is a superspace. CV is TV0 direct from TV1, where CV0 is just the summation of CIV0 and CV1 is the summation of CIV1. We make the summation of all odd parts and make the summation of all even parts. And then we get a superspace again. But this superspace actually is a unital associative superalgebra if I introduce a product and this PV. Okay? And we can define the product and CV using the bilinear extension of the solvent. Okay, my TV is direct on TIB. So if I want to define a product on TV, it is enough to get some element of TIB, some element of TJB, and tell you what is the product. And then I bilinearly extend it to entire TV, right? I define one up to 1, and I will show for a moment the product just by that. It is x1 x for all x belong to TV, because I have, you remember, T0 is F and F is F1. That 1 is the unit of F. Okay, so this TV has a unit. Its unit is just the unit of F, and I define 1x to be x for all x belong to TV. And if I have x1 tensor xn as a typical generating one of the elements of the generating set of T and V, and then I want to make the product with another element in T and V. I just define it by juxtaposition. I just put this together. So I have x1, xn, y1, ym, and it is an element of Tn plus mv. I get an element of Tn, an element of Tn, and then define its product, which is an element of Tn plus m. Okay? And then we extend it bilinearly, and the TV together with this product is a unital associative superalgebra. And from the definition, it is clear that compatibility happens. You remember, I told you, if A is a superalgebra, Aj must be an element of Ai plus j, and I defined it in the way that such a thing happens. Okay. Let's look at another definition. A superalgebra A with product star is called a least superalgebra if a star is anti-commutative and the Jacobi superidentity is satisfied. Okay? If the product is anti-commutative and the Jacobi superidentity is satisfied, we say that we have a least superalgebra. And it is usual to use bracket instead of a star when we are talking about a least superalgebra. So we usually denote the product of a least superalgebra by brackets. So A is a superalgebra if what is anti-commutativity y equals -1 degree x degree y x and x y z equals x y z -1 degree x degree y x z. For all x, y belongs to A0 union A1 and Z an element of A. It is a least superalgebra. Okay? Any question? Cool. And the exercise show that if A star is an associative superalgebra, then A together with bracket from A times A to A, mapping AB to AB -1 degree A degree B BA, for AB belongs to A0 union A1 is a least superalgebra. This is superalgebra is denoted by a law. So, using an associative superalgebra, we can get a Lie superalgebra. And I gave you some examples of associative superalgebra. Using those examples, you can get some examples of these superalgebras. As the first example, suppose that E is a superspace then right now I told you that TV is a unital associative superalgebra. So TV bar is a Lie superalgebra. Another example, suppose that M and N are two positive integers. You know, the set of all square matrices of dimension m plus n together with the usual product of matrices is an associative superalgebra. So G of F Mn, which is m plus n, m plus n f bar, is a Lie superalgebra. Okay. Another example, suppose that E is a superspace I told you that when we have two superspaces V and W, the set of all linear transformation from V to W is a superspace. So the endomorphism of V is also a superspace. Together with the function composition is an associative superalgebra, and so GLF V0 V1, which is the bar of endomorphism V, is a B algebra, B superalgebra. Okay. Okay. When we have an algebraic structure, we can talk about ideal and sub-algebra in our sense, and we can define them now. Let's have a definition. Suppose that A is a superalgebra. Let me put at first on this. Suppose that E is a superspace subset W of B is called a sub-superspace if the first condition is that W must be a subspace of the usual vector space, okay? But we need something in superalgebras. Okay, if RA plus B is an element of W for all scalar in F and AB belongs to W, and the second one is that W is direct sum of W B0 and W B1. And it is equivalent to this. B for B belongs to V. V is an element of W. B is an element of W if and only if B0 and B1 are elements of W. Okay? Two. Suppose that A together with a star is a superalgebra and B is a sub-superspace of A. We say B is a subalgebra of A if AB is an element of B for all A and B elements of B, and a sub-superspace I is called an ideal ideal of A if AB and BA are elements of I for all A belongs to A and B belongs to I. Okay? And you can guess what is the next story. When we have an ideal, we can talk about the quotient, right? But before that, let me tell you about something else. We know that the intersection of ideals is again an ideal, right? And suppose that A is an associative or a least superalgebra and X is a subset of A0, A1. Set Xi to be the intersection of all I when I is an ideal of A. This notation is the notation for the ideal and all the ideals containing this X. Then this Xi is an ideal of A which we call it the ideal generated by X. Note that I told you that the element of X must be homogeneous. They are elements of A0 union A1. And we need this condition because you remember, I told you, when we want to talk about an ideal, the ideal must be a superspace at first. Okay, sub-superspace. And as we want to have a sub-superspace, we need to start with a homogeneous element to be sure that this intersection that we write here and everything that we have are satisfied, and then we can get an ideal. Okay.
Sorry, what's the meaning of the subscript I for X?
Just for ideal. Because sometimes we define this as a subalgebra, but here I want this for ideal. Okay. Suppose that L is a least superalgebra. I told you, sorry, there's a question here. Oh, someone asked about the record. Okay, but it is recording, yeah?
Yeah, I think so.
Yeah. Yes. Okay. Suppose that L is a V superalgebra, and I told you when we have a superspace, we have TV. If V is a superspace, we can talk about TV, okay? And now we have a V superalgebra. A V superalgebra is a superspace at first, so we can talk about TL. L is a V superalgebra, and consider CL. Okay. We know that CL is a unital associative superalgebra. Okay. It is a unital associative superalgebra, and then we can make a specific ideal of this associative superalgebra. Set X to be all elements like this. Bracket of xy minus x tensor y plus -1 degree x degree y tensor x when x, y are elements of L0 union L1. Okay? And as x and y are elements of L0 and L1, this is a subset of L0, L1, and then set UL to be TL over xi, right? And it is the quotient of TL over an ideal if A is an associative superalgebra and I or a Lie algebra. And I is an ideal of A, then A over I, A0, A1 over I0, I1, it is A0 plus I over I plus A1 plus I over I, but it can be proved that it is A0 plus I over I, direct sum A1 plus I over I, which is isomorphic to A0 over I0, A1 over A1. When we have an associative or a least superalgebra, and I is an ideal, the quotient space is also a superspace. And then we can define the product on A over I in a usual sense. To AB plus I is an associative superalgebra or a leaf superalgebra, respectively. If we start with an associative superalgebra, we get an associative superalgebra, and if we start with a leaf superalgebra, we will get a leaf superalgebra. And here we have TL. TL is an associative superalgebra. We have an ideal here, so I can talk about the quotient of TL over this ideal, and we get this UL. This UL is called the universal enveloping algebra of F. And to study the representation of a leaf superalgebra, this UL plays a very important role. Okay? You want to have a 1 minute break? Someone asked to send the record to him.
I think the recording is uploaded from the ICTP channel.
Okay, maybe. It was enough. Okay, let's continue. Suppose that A and B are two superspaces, and phi is an element of linear homomorphism of A to B. Okay? Please be careful. Phi is called an algebra homomorphism, or it's better to say a superalgebra homomorphism if phi is an element of home F A, B, 0. You remember, homomorphism A, B is a superspace. There are some odd parts, there are some even parts. And when we say that we have a superalgebra homomorphism, at first this phi must be of degree 0. Okay? And then phi AB equals phi A, phi B for all AB belong to A. And you know that this product is product in A, and this product is product in B. Now, suppose that L is a Lie superalgebra and recall CL and U. CL is a unital associative superalgebra, and UL that was the quotient of that TL is also a unital associative superalgebra. And you know that C1L is a subset of TL, and C1L is just L. So L is a subset of TL. The map iota from L to UL bar. I told you, when we have an associative superalgebra, we can make a Lie superalgebra that we call it A bar when A was our algebra. And here, our associative superalgebra is UL, so we can talk about UL bar. And here we have a map from L to UL bar. And what is the action? We send X to I use some other notation. UL is CL over XI. For simplicity, I show A plus XI just by A tilde. Okay? And I map X to X tilde. The map iota is in the algebra, the superalgebra homomorphism. Okay, it's clear. We have UL. UL is the quotient of TL over an ideal. For simplicity, I wrote A tilde instead of A plus XI, and I just map X to X tilde, and it has meaning because L is a subset of, I told you, L is a subset of TL, so for an element of X, X tilde has meaning, okay? And it's proved that the map iota is a Lie superalgebra homomorphism, okay? We start with a Lie superalgebra, then we get an associative superalgebra, then we make the bar, and we have a Lie superalgebra here, and this map is a Lie superalgebra homomorphism. a very important property for the universal enveloping algebra of L that shows you why we call it universal. Please be careful about something that I want to avoid. Assume L is LD superalgebra and recall I will start from L to UL bar. If A is a uniton associative superalgebra and F from L to A bar. A is an associative superalgebra, but A bar is LV superalgebra. And if F from L to A bar is a V superalgebra homomorphism, then let's draw a diagram. We have L here, we have UL here, we have A here, and F here, and iota here. And you can guess what will happen. We have a map from L to A, but this map is a V and V superalgebra homomorphism from L to A bar. And we get that there exists a unique associative superalgebra homomorphism F tilde from UL to A such that this diagram is commutative. It means that F tilde iota is F, and F tilde has this property that maps 1 to 1. And this is a very important property of this universal algebra. One more time. We have L here, iota, UL. This F is a map from L to A. A is associative. This F is a map from L to A, but if we consider it as a map from L to A bar, it's a V superalgebra homomorphism, and then we get an associative algebra homomorphism from UL to F. And it is unique and maps 1 to 1. And there is a theorem. The superalgebra homomorphism iota from L to UL bar is injective. This map is called the canonical embedding. embedding, it means that you can consider L as a subalgebra of UL bar, right? And another theorem, if L is a weak superalgebra and G is a subalgebra of L, I use this notation for subalgebra, then we have UL and we have UG, then UG is embedded UL. So we can consider UG as a subalgebra of UL. Okay? Any question? Next topic. Let's look at another definition, a very usual definition. Suppose that Li, when I runs over an index set, is a class of these superalgebras. Then we can form the vector space of vector spaces. But this direct sum is a superspace at first, because it just consider L0 to be the direct sum of the even parts and L1 to be the direct sum of odd parts. And then just point-wise, we can define a bracket on L, so L will be a least superalgebra. L together with point-wise product is a superalgebra called direct sum of Li. Okay, just if you have two elements like this and yi, bracket is just this. I also want to mention something. Suppose that L is a Lie superalgebra. So what we have xy equals minus 1 degree x degree y x, and we have xy z equals x y z minus y z when x y are homogeneous and z is an element. Suppose that x, y, and z are elements of L0. What happened? X and y and z are elements of L0. So degree x and degree y is 0. So what we get? Bracket of xy is just minus yx. And here we have xyz minus yxz. It's just a Lie algebra. Okay? So when we have a superalgebra, the even part is a Lie algebra. L0 is a Lie algebra. And the second point, define a star from L0 times L1 to L1. And for xy, belongs to L0 and z belongs to L1, we have x, y, s star z. I didn't define this. Maps x, y just to x, y. And it is a map from L0 to L0 times L1 in L1, because you remember we have a superalgebra and the bracket of L0, L1 is a subset of L1. So it is really a map from L0 times L1 to L1. So we get an element of L1 when x is an element of L0 and y is an element of L1. Now we look at x, y, s star z. What we have, it is x, y, z. It is x, y, z. As x, y are elements of L0, this guy disappears. So we have this. And what is this? It is an element of L1. It is an element of L1. So here we have x star, y star z minus y star. What is this? A module. L0 is a Lie algebra and L1 is a module for L0. When we have a Lie superalgebra, L0, the even part is a Lie algebra and the odd part is a representation or a module of L0. Okay? And so representation theory of Lie algebras is very important to study these superalgebras. Okay, any question? The main aim of the lecture is representations of affine superalgebras. So at this time, I want to tell you what is a module for an associative or a Lie superalgebra. Assume A is an, let's suppose it is unital, is a unital associative superalgebra and D is a superspace. We say B together with a bilinear map I denoted by dots from A times B to B is an A module. If first of all, AI J is a subset of BI plus J on J belongs to 0 and 1. And second of all, A, B, B equals AB, B for A and B belong to A and B belong to B. And then we want 1A, 1B to be B for all B belong to B. We call such a thing a module over A or an A module. And some modules are defined in a natural way. When we say that W is a submodule of B, we want that W respects this decomposition, so it must be a superspace, and then just preserve the action of the module. Okay? And when we define submodules, then we can define the irreducible modules. And irreducible modules are also have the natural definition, just the only submodules are the trivial modules, and we want that module not to be 0. Okay, and as an easy example, if A is a uniform associative superalgebra, and B is a subalgebra of A containing 1, then A together with the restriction of the product B times A is a B mod. And it is clear. A is an algebra, so we have a map from A times A to A, and B is a subalgebra of A. If there is this S star to B times A, we get a map this way, and as we suppose that we have an associative algebra, this S star restricted to B times A, satisfying all these properties, and then it is a B mod. And when we define submodules, we can talk about the quotient of modules. And V is an A module. Assume W is a submodule of V. Then V over W, which is V0 plus V1 over W, and it is V0 plus W over W, V1 plus W over W, but this sum is a direct sum. And it is isomorphic to V0 over W0, direct sum V1 over W1. This superspace, together with this action from A times V over W to V over W, that's A V tilde maps to A V tilde. You remember, I told you by V tilde, I mean the V plus W, an element of V over W. It is also an A module. That we call it the quotient module. And as an exercise, show that if K is a submodule of V over W, then there is U, a submodule of V, which contains W, such that K is U over W. All submodules of the quotient are again a quotient. And now let's define a module for a least superalgebra. Suppose that L is a least superalgebra superspace. B together with a bilinear map dot from L times V to B is called an L module if at first Li Vj must be a subset of Vi plus j, and then x y v must be x y v minus -1 degree x degree y y x v. I, j are elements of 0, 1, and here x and y are elements of L0, L1, and v is an element of v. Okay, this is the definition of an L module when L is a least superalgebra. And when we have L modules, we can define submodules. When we define submodules, we can define irreducibility. And when we say that a module is irreducible, it means that it's not zero, and the entire V is the only submodules. Okay? Let's look at an example. Suppose that L is a least superalgebra and G is a subalgebra of L. Then a star from G times L to L, mapping its Y to the bracket of its Y defines a G mod. Yeah. It is very easy to see that these conditions are satisfied. The first one is clear because L is a least superalgebra and G is just a subalgebra of L, and the second one is just the Jacobi superidentity. It is a very easy exercise that you can write it down. Just okay. What time is it? Let me see. Let's another definition. And again, when we have modules and submodules, then we have the quotient modules, okay? Suppose V is a module over a least superalgebra L, and W is a submodule of V, then the quotient is space V over W together with W to V times W max X V tilde to X V tilde is an L module of the quotient module. And again, you can see that all submodules of this quotient is just a quotient of U over W, when U contains V and is a submodule, contains W and is a submodule of V. Okay. I think it's better to stop now and then continue tomorrow at 10.